Hi, in today's video, we'll have a look at hypothesis testing when carrying out multiple linear regressions. So in the multiple linear regression model, we assume that yi is equal to alpha plus beta 1 times x1 plus beta 2 times x2 plus ui. And very often we'll be in a situation where we want to test hypotheses regarding the values of the parameters alpha, beta 1, and beta 2. And very often, actually, we'll be trying to see if the coefficient beta 1 or beta 2 is equal to 0 or not, because that will be an indication of whether x1 has an impact on y1 or if x2 has an impact on yi. So we may want to test the hypothesis that beta 2 is equal to 0. As always, when you want to carry out a hypothesis test, you need to start by setting your null hypothesis and your alternative hypothesis. In this case, my null hypothesis is that beta 2 is equal to 0. Okay, and remember that a null hypothesis always has an equal sign. And the alternative hypothesis in this case is just that beta 2 is different from 0. Okay, so it's just the negation of my null hypothesis. So when we ran our regression, we got a parameter estimate for beta 2 of 0.171. And we want to test whether B2 is significantly different from 0. Okay? So obviously 0.171 is different from 0. But remember that this is just the value that we got from one sample. But if we had gotten a different sample, we would have gotten a slightly different B2. And we want to know whether it's compatible with the null hypothesis that the true B2 is equal to 0. And do we have enough evidence to say that actually beta 2 must be different from 0? So we therefore calculate the t-statistic, and remember the t-statistic always follows the same pattern. So you have your estimate, B2 in this case, minus beta 2, so that's my null hypothesis, divided by my standard error, okay? And the standard error will just be given to you in your regression table or in your statistical software, so you don't need to care too much about that. But just know that it is basically the estimated standard deviation of our estimator. So in this case, B2 is equal to 0.171 minus my null hypothesis, in this case 0, because we assume that beta 2 is equal to 0 as our null hypothesis, divided by my standard error. And I get 3.31. Now, we know that our test statistic has a t-distribution with n minus 3 degrees of freedom, assuming that the null hypothesis is true. So remember that with a t-test, when we want to calculate the number of degrees of freedom, we just look at our sample size, so n, minus the number of parameters that we estimated. And in our regression model, how many parameters do we estimate? Well, there's alpha, there's beta 1, and beta 2. So that's 3. So here, that's why we have n minus 3 degrees of freedom. Now, if n is very large, let's say above 100, it's not going to make much of a difference, the fact that we're looking at the t-distribution and not the standard normal distribution. Now, since we know the distribution of the test statistic under the null hypothesis, we can calculate the p-value, okay? And so what is the p-value? The p-value is just the probability that we would have obtained a more extreme test statistic than the one that we got. Okay, so for example, here we had a test statistic that was equal to 3.31. So I'm going to look at here, 3.31, and I'm saying, well, what would be more extreme than 3.31? Well, anything greater than that would be more extreme. And if I go on the other side and do the same thing, but this time minus 3.31, what would be more extreme? It would be everything that is to the left of that value. Okay? And so here we're just saying it's more extreme if the distance from zero is greater than what we've observed. Okay? So that's why we're looking both at the right-hand side and the left-hand side. Okay? That's always what you need to do when you're looking at a two-sided test. And here, if we calculate that area, we can see that it's super, super small. So here, I've just put in those box a magnified image of what we see here. And so if I calculate this black area plus this black area, we get a value of 0.001. Okay, this is very, very small. It's definitely smaller than any reasonable significance level that we may choose. So the convention is very often to choose a significance level of 5% or 1%. But even if we choose 1%, we would reject the null hypothesis that beta 2 is equal to 0. Okay, so we conclude that beta 2 is significantly different from 0. So that's it for today's video, and in the next video, we'll have a look at how we can test multiple hypotheses at the same time.